Ah, what a beautiful day. The sunlight is making me glow even more. I'm like a radiant goddess. Wait, am I beautiful? Is that a statement? Or, hold on. Statement should be declarative, not questioning. Or am I presenting an argument? Ah, I'm so confused. Maybe I just need to jump on the pool.
Hold on, Yan. You're just a tad confused.
Where on earth is that sound coming from?
Do you trust me?
I guess.
Okay, calm down. Take a seat on that bushy grass. Will help you unravel all these confusions bubbling in your mind.
Hello, everyone. Today, we're delving into the fascinating world of logical statements and argument structures. So grab your thinking cups as we unravel the conventions for representing statements and logical constants.
Let's first examine what a simple statement means. By definition, it contains no connecting words. In FDL, these connecting words are also called logical constants. Additionally, simple statements are represented by single capital letters. We have four logical constants that we conventionally use to represent statements. Technically, a conjunction is denoted by the word and an inverted V or sometimes a dot. Next, we have the alternation, often called disjunction, which is the opposite of conjunction and implies the phrase either or. Symbolized by the letter V. The third logical constant is the conditional, represented by the symbol pointing to the right and implied by if and then. Lastly, we have the biconditional, denoted by the if and only if symbol, represented by three stacked lines or usually an arrow pointing in opposite directions. Now that we're clear on that, let's move on to compound statements. A compound statement is a sentence that consists of two or more statements separated by logical connectors. Usually, the two statements are denoted by P and Q respectively. Let's now take a quick look at the following statements.
Plato is a philosopher, represented by P. Aristotle is a philosopher, represented by Q. First, for conjunction, Plato is a philosopher and Aristotle is a philosopher. Then, Plato and Aristotle are philosophers. Next, alternation. Either Plato is a philosopher or Aristotle is a philosopher. Then, either Plato or Aristotle is a philosopher. Third is the conditional statement. If Plato is a philosopher, then Aristotle is a philosopher. And lastly, the biconditional statement. Plato is a philosopher if and only if Aristotle is a philosopher.
How are you, Yan? Do you understand the concept now?
Yes, I do. But what if the statements were nullified and taken in a negative way? Like when I say that I'm not beautiful.
Oh no! Don't think that way. But what you have said is what we call negation. We represent negation by the tilde symbol, which means not. We can negate simple statements or compound statements. If you see a negation sign before a statement, it does not necessarily mean that said statement is false. Are you tired already?
No! I'm actually enjoying it. I'm craving for some more.
Oh, really? But wait, I think I need to pass it on to my friend named Sian.
Oh, how are you doing, beautiful Yan?
I'm doing great.
Let us now take an inside look at the truth values of compound statements by first familiarizing ourselves with the three principles governing the truth values of statements. The principle of identity implies that a statement implies itself. It is always true, and its true value remains stable over time. The principle of excluded middle states that the true values of any statement are either true or false only. The principle of non-contradiction prevents assigning two truth values to a statement simultaneously. To better understand it, let us consider these examples. For the principle of identity, by its definition, we suppose that puppies are indeed young dogs. So, if P is true, then P is true. If P, then P. Alternatively, if puppies are not young dogs, then if P is false, then P is false. If not P, then not P. Therefore, this statement is always true. This is what we call tautology. Next is the principle of excluded middle. If P is true, we automatically suppose that its negation, not P, is false. P and not P are truth functionally related. Alternatively, if we affirm that P is false, then its negation, not P, is true. P or not P is always true because in all possible substitutions of its true value, it remains true. Therefore, P or not P is a tautology. Lastly, the principle of non-contradiction. The conjunction of the statement P and not P is self-contradictory. To make it tautology, this conjunction should be nullified, thus, negation of the quantity P and not P. Allow me to walk you through each truth table of the logical constants. Let us have first the negation and double negation. As what you can infer from the table, the column on the left is the total opposite of the column on the right. This means that if P is true, then its negation, not P, is false. Likewise, if P is false, its negation is true. It is false that young dogs are not puppies, or not P. P is denied twice, a double negation. In double negation, it implied its affirmation. However, if the statement is denied thrice, it is once again nullified. If denied 4 times, it is again affirmed. From the truth table of conjunction, we can say that P and Q is only true provided that both P and Q are true. The conjunction set of premises is only true when all its elements are true. If at least one element is false, then the whole premise set is false. Let us now proceed to the truth table of alternation. P or Q is only false if P and Q are false. To formulate a true alternation set of premises, at least one of its elements should be true. Next, we have the truth table of conditional. The conditional is false only if the 10th part or the consequent Q is false. We should also take note the logical form of deductive argument, denoted logically isomorphic, with the logical form of a conditional truth table. We have 4 cases. Case number 1, if true, then true, it is a valid argument. Case number 2, if true, then false, an argument will be invalid. Case number 3, if false, then true, the argument is valid. And the last case is that if false, then false, the argument is valid. In short, An argument is only invalid when the premise set is true and the conclusion is false. This relates to a conditional truth table where the set is only false when its antecedent is true and the consequent is false. In a valid argument, if the premises are true, the conclusion cannot be false. Finally, the truth table of biconditional. A necessary condition is that P is true if Q is true. A sufficient condition that P is true only if Q is true. When both elements P and Q are true or both P and Q are false, the biconditional is true. Additionally, we have what we call negation of compound statements, wherein the same procedure holds for other compound statements, such as the alteration, conditional, and the biconditional.
As we go through this, I want to discuss how we can represent arguments. Representing arguments is an indispensable skill in proving the validity of the truth table method. We represent an argument to, first, reveal its logical structure, and second is to isolate it from its content. To isolate the logical structure from the content of the statement is the purpose of representing a compound statement. An argument can be represented the way you can represent a statement, regardless of whether it is a simple or compound statement. We have 4 steps in representing arguments, so we are going to use this example to show how to apply the steps. For our first step, represent the simple and compound statements. The compound statement is the whole statement, which is the if we can represent statements, then we can represent arguments. And the simple statements are we can represent statements, and therefore, we can represent arguments. To show the simple statements, we divided the compound statements. Second, represent the premises by using letters. For our compound statement, the word represent is represented by capital R, capital S for statements, and capital A for arguments for simple statements. Third, represent the conclusion with an indicator, which is the 3 dots. In our example, we write it as the 3 dots, and therefore, we can represent arguments. And for our last step, represent the argument by revealing its logical structure. We can represent it in 2 ways, either vertical or horizontal representation. In the horizontal representation, the indicator or the 3 dots that represents the conclusion was transformed into the symbol of the conditional, which is the arrow pointing to the right. The first premise states a conditional. The second premise affirms the antecedent of the conditional. And the last premise, which is the conclusion, is deduced from the 2 premises. The logical form of an argument can be classified as valid or invalid. It is considered valid if content is not part of the analysis of validity. Logicians call this form modus ponens, which means that the strength of a deductive argument rests solely on the logical form and not on the content of the argument. On the other hand, it is invalid if the content is part of the analysis, meaning to say, if an argument form has a true premise set and a false conclusion, logicians call this a fallacy of affirming the consequent.
Let us now take a look on the characteristics of all valid argument form. There is no case in which the premise set is true and the conclusion is false. If an argument form has a true premise set and a false conclusion, it is invalid. The logical form of all deductive argument. We use the 3 dot for vertical representation, while the arrow pointing to right for horizontal representation. The premise set 1 and 2 are joined by a conjunction, and the therefore indicator, which is the tree dot that represents the conclusion, was transformed into the symbol of the conditional, which is the arrow pointing to right. The main connective of the argument is the conditional. I think Yan is overwhelmed with all the information that we are sharing. Am I right?
Kind of. But I'm eager to know more, particularly about the basic deductive argument forms.
Basic deductive argument forms. The ability to distinguish valid from invalid argument form is an indispensable tool so that you could do the same to more complicated argument structures. The conditionals. Example of a two-true statement. Amphibians are animals and birds have feathers. Let A represent the animal and B represents the birds. Okay, let's start with conjunction. Conjoining two true statements preserves the truth value of the conjunction. Premise 1, amphibians are animals. Premise 2, birds have feathers. Therefore, amphibians are animals and birds have feathers. Next is simplification. If conjoining the two truth statements preserves the truth value of the conjunction, then separating their conjuncts preserves the truth values too. As such, premise 1, amphibians are animals and birds have feathers. Premise 2, therefore, amphibians are animals. Or we can also say, premise 1, amphibians are animals and birds have feathers. Premise 2, therefore, birds have feathers. Another example of a two-true statement. Whales are mammals and snakes are reptiles. Let W represents the whales and S represents the snakes. Alternation. From the two true statements, you can create an alternation. Either whales are mammals or snakes are reptiles. In conjunctions, you can validly infer any of the conjuncts. However, in alternations, you cannot, since an alternation is true even if only one of the alternants is true. Subtracting an alternative. Invalid argument structure listed below. For our last set of example of a two-true statement under the basic deductive arguments, true, FPJ is running for president. False, Danding is running for president. Let F represents FPJ and D represents Danding. Adding an alternative, forming a valid argument. Premise 1, FPJ is running for president. Premise 2, therefore, FPJ is running for president or Danding is not running for president. Remember, an alternation is true if only one of the alternants is true. It is false if both alternants are false. Adding a conjunct. If the statement is true, then you cannot add a conjunct because the statement might be false. Suppose R is true, then this structure. Premise 1, R. Premise 2, therefore, R and L. Since R is true, then the given structure is an invalid argument. Remember, we can only form a conjunction if both statements are true. Disjunctive syllogism. Detaching an alternative is valid when you know the alternation is true. Not because both alternants are true, but one or the other is false. Denying an alternative. An invalid argument that is often confused with a disjunctive syllogism. Example. If you know that the statement that FPJ is running for president is true, you cannot infer that the statement that Danding is running for president is false because it can still be true. On the other hand, if you know that the statement that Danding is running for president is true, you cannot infer that FPJ is running for president is false. Remember, the argument denying an alternative can easily be confused with the valid argument of disjunctive syllogism.
Oh, whoa! Here's a quick overview of our Math 10 topics. Philosophy is something, huh? I'm starting to like it even more. Would you like to give me some more? Brainy Sian?
I would love to. Let's proceed with complex argument forms, which I think you have also tackled in your Math 10. Complex argument forms. Modus ponens and affirming the consequent. For modus ponens, we have premise 1, if R, then L. Premise 2, R. For premise 3, therefore L. For affirming the consequent, premise 1, if R, then L. Premise 2, L. Premise 3, therefore R. Modus ponens and affirming the consequent is an invalid argument. Modus tollens and denying the antecedent. Modus tollens is the counterpart of the valid form of modus ponens, while denying the antecedent is affirming the consequent or denying the antecedent. For modus tollens, we have premise 1, if R, then L. Premise 2, not L. Premise 3, therefore not R. For denying the antecedent, we have premise 1, if R, then L. Premise 2, not R. Premise 3, therefore not L. Modus tollens and denying the antecedent are also invalid argument. Next, we have detaching the consequent. We cannot infer the consequent because the consequent and antecedent of conjunction can both be false, yet the conjunction can still be true. Premise 1, if R, then L. Premise 2, therefore not R. We also have the hypothetical syllogism, built around a hypothetical statement which takes the form if, then. It is not entirely hypothetical, but one of its premises is premise 1, if R, then L. Premise 2, if L, then C. Premise 3, therefore, if R, then C. Fallacy of misplaced middle. A formal policy is committed when the middle term is a categorical syllogism is not distributed in either the minor premise or the major premise. Premise 1, if R, then L. Premise 2, if C, then L. Premise 3, therefore, if R, then C. Constructive dilemma affirms the antecedent R and L of both conditionals. The logical form of a constructive dilemma is a combination of two modus ponens. We have premise 1, R or L. Premise 2, if R, then D. Premise 3, if L, then C. Premise 4, therefore, D or C. On the other hand, we have destructive dilemma. Denies the consequent not D and not C of both conditionals. The argument structure of a destructive dilemma is a combination of two modus tollens. Premise 1, not D or not C. Premise 2, if R, then D. Premise 3, if L, then C. Premise 4, therefore, not R or not L. The two fallacious forms of dilemmas. Pseudo-dilemma 1 denies the antecedent. Premise 1, if R, then D. Premise 2, if L, then C. Premise 3, not R or not L. For premise 4, therefore, not D or not C. Pseudo-dilemma 2 affirms the consequent. Premise 2 and 3. Premise 1, D or C. Premise 2, if R, then D. Premise 3, if L, then C. Premise 4, therefore, R or L.
With that, let us represent an argument and learn to construct a truth table. Module 7 is all about constructing a truth table. So, this method contains 4 simple steps. For our first step, represent the argument in horizontal form like this. Second, count the number of simple statements in the argument. Third, construct a table for all the possible substitution instances of truth values of R and L. And for our last step, assign truth values to the statement in the argument structure. Make sure to show the truth values, premise set, conclusion, and the argument.
OMG, it is already time. I need to change my clothes for my swimming lesson. I will be drawn with so much enthusiasm from the fun-filled learning that we had.
And there we have it. We've learned so much today. What a nice exploration into Acuna's Unit 3, Modules 2, 3, 4, 5, 6, and 7, discussing about logical statements and argument structures.